constant. It's not just a weak strong coupling duality. It also involves the large n limits, which makes it a bit non-trivial than normal. Because of this duality here, if we have some exact results for Wilson loops, we can get some exact predictions for the Hopf loops with chiral primaries. And there are actually such results for expectation values of chiral primaries in the background of a Wilson loop, and we can use that to get predictions for the same correlation function loop. And of course, localization only works for protected quantities. If you really want to have new correlation functions of non-protected quantities, then you have to resort to integrability. Some of our work comes into play. Okay. So what I will be looking at is correlators between this 't Hooft loop and the chiral primary. And due to conformal invariance, it's bound to take this form here, where delta is the conformal dimension of the operator that I insert in the background of the Wilson loop. And to begin with, let me look at operators like the simplest possible chiral primary, which is just a trace of some complex L. And actually, the expectation value of this operator in the background Wilson loop is known exactly from a localization computation. So, of course, the localization was prescribed by Pesto originally, but for this particular setup, it was worked out by Okayama and Simonov. And they simply show that all orders in lambda and all orders in n, the function is given by this expression here, where the L's are Laguerre polynomials. And this is actually for a chiral primary at the center of the Wilson loop. And of course, this is something which we can use to get a prediction for what the correlation function with the Hooft loop should look like. Okay, again, it gives some testable prediction for the one-point function of protected operators, but for operators we don't get anything, then we have to use integrability. But now let me look at what you actually get from this computation. Okay, so as I said, S-duality, it mixes strong weak coupling and large n, so it's not completely trivial question for the 't Hooft loop. But what you can do is to use an integral representation of the Laguerre polynomials and then do a large n saddle point approximation. Then you will get a result in the large n limit, but it contains all powers of the coupling constant. That we have done together with Konstantin, and that results in this expression here for the one-point function. So there's this Bayes-time dependence which is necessary, and then there are these two terms here. And they are quite simple. You can expand, of course, in lambda for small lambda and see what the derivative series look like. And people coming from integrability will probably recognize that this looks like something which consists of wrapping corrections and non-wrapping corrections. So to those who don't come from that community, wrapping corrections are corrections which correspond to Feynman diagrams which involve all fields in the operator, while the non-wraps do not. Okay, but we can try to expand this for small lambda, and with the first term again is very simple, just looks like this. You can also see that it's easy to recover at least the leading order term here, because I just have to insert the classical value of the scalar field, which in my units 1/2r, and that gives this prefactor. Then there's something coming from a normalization, and then the 1. So okay, the normalization works. But if you want to check the higher, then you really have to quantize the theory around the monopole background and do an honest conservative computation. Okay, try to see how that works. But before quantizing, we look a little bit about at the structure of the higher loop corrections, because you can of course try to expand this one-point function for various operators of varying length. So subscript here is a length, and this is the space-time independent part of the one-point functions. And here I have given the part coming from the first term in the expression in black, and the part coming from the second term in the expression in blue. And one observes a quite curious structure here. All the point functions have a perturbative series which terminates after a finite number of terms. Quite unusual, of course. You sometimes see it in local, but here there's nothing more than these few first terms. But then, even length of the one-point function, there will be additional terms coming from the second term, and they actually start out exactly at order lambda to the 2 characteristic of wrapping corrections, which involve all fields. So the non-wrapping part truncates for all L. And this is actually a structure one sees in different defect setups, also for the D3 probrane setup, and for Gucker-Witten defects, that you have actually truncation without any wrapping corrections, which is even more simple. It was actually something which was which triggered our investigations here. But what I would like to do is to try to understand where non-wrapping corrections come from. I can do that with perturbation theory, of course, and then it would be to try and understand these wrapping corrections, which is an eternal problem in integrability. Okay. Understand the perturbative series. I need to quantize, but first say that I can actually write down a closed form of these non-wrapping corrections, those which terminate. And it's simply a finite power series, as I said. And then it terminates at the order which is L over 2, where L is an operator. It has some perturbation, some coupling constant dependent term here, and then there's some combinatorial factor. And we want to recover this expression quantizing around the monopole. And as a future, we would also like to understand the remaining part, which comes from wrapping corrections. Okay. Yes. So around the monopole configuration, it's in principle a textbook exercise, but it's a little bit involved. So you have to expand around the classical fields and look at the fluctuations. Of course, there will be some cast term which mixes the fields, and you have to diagonalize it. So my classical fields, they had only a non-vanishing in the upper left-hand corner. So if I write them in this form here, there will be a part in the lower right-hand corner which are not affected by the classical wefs, and then there will be a small part in the upper left-hand corner which is also not affected, actually. But these parts in the first row and the first column, they are heavily affected by the classical fields. Okay, then I expand. I get a new, rather complicated quadratic part of the action, which I need to invert to find my propagators. But to gauge fix, that's a story in itself, and I'm not going to that. To invert the quadratic part of the action and determine the propagator, I actually have to solve some very, very acute quantum mechanics which can be solved exactly. So just to make it clear, if I write my classical quadratic part, or not classical, if I write the quadratic part of my action for some fields phi in this way here, propagator at this place, then I can find my propagator by solving the problem for this operator d to the minus 1 here, and then do a spectral sum over eigenvalues and eigenfunctions as a classical way to find the propagator. And that is, of course, just a quantum mechanical problem. You need to diagonalize the operator, finds its eigenvalues and eigenfunctions. And that then is relevant only for these field components in the first row and the first column. Okay, and what do these quantum mechanical problems look like? Well, they're actually very, very nice. They depend a little bit on the fields. There are some fields for which the problem simplifies. They are classical fields which don't get wefs, and one part of the gauge field are ghost fields. And for those fields, I simply have to solve the problem which consists of having a scalar particle in a monopole potential. And that is actually exactly what Dirac solved in 1931. And there are some really beautiful papers, both from the 30s and the 40s, which solve this I mean, they knew exactly the same language as we do today. It's really curious that it's 100%. It's very, very clear. Okay, so that is solved, and you can find the propagators by spectral resonation. Then there's the propagators for the A field components. For that case, you have to solve a problem which consists of a scalar in a monopole potential, but coupled to a spin 1 part. And that has actually not really been solved before, or it had not been solved, but the spin 1 particle alone was considered by Olsen, Osland, and Wu in 1990. But it turns out when you couple to, which you're doing here because of supersymmetry, then you actually get a neater problem. The solution is more beautiful, which I think reflects the underlying integrability and eventually the underlying supersymmetry. For the fermions, it's also a quantum mechanical problem, and that consists of fermions in some potential. The standard case was solved back in '77 by these people, but in this case we have a non-standard potential because we have something to the scalar. But again, it can be solved exactly. Okay. Yeah. So I will not go through the solution, although it's very beautiful. But as I said, you find the eigenvalues and the eigenfunction, and you do this spectral resummation. So scalar propagator for those that I called easy fields look like. And I show it because it has some really nice symmetries that you could have expected. So first of all, the whole problem, it has a flavor of a particle in a central potential, of course, and you can introduce some angular momentum operators with a usual SU2 commutation relation that allow you to diagonalize the problem. But in this case, as we all know in school, that some of the angular momentum is actually carried by the magnetic field here. So there is a spectral flow, so that a scalar particle actually has a half integer angular momentum in a monopole potential. But otherwise, you solve in terms of some spherical harmonics, which are not the usual but so-called monopole spherical harmonics, and they involve Jacobi polynomials instead of Laguerre polynomials. So that takes care of the physical part, and then there's a radial and time-dependent part, which is taken care of by some base functions. And so here in the denominator are the eigenvalues, the time part coming from the time-dependent part and the space-dependent part, and we have to integrate over all these eigenvalues and sum over. And that can actually be simplified. You can do the integral, and you can do the sum, and then you end up with some mode decomposition, so to say, where the angular part is taken care of by these Jacobi polynomials, and then the space-time part, the radius, the distance to the defect, and the time is actually in AS2 propagator, which is actually exactly what you would expect from the system. You have this 't Hooft line, and it effectively behaves as a ADS2 space. So you get an ADS2 propagator and then times some spherical part. And it's very nice to see it coming out from the actual quantum mechanical computations. And everything is known in closed form, and you can also dimensionally regularize and consider this in ADS D dimensions instead of ADS2. Okay. Then there were some complicated fields where you have a large degree of mixing, namely between the scalar and field. And you have to write down what is the mixing matrix for these fields. So this is what it looks like. And it's a 4x4 matrix. There's one scalar and 3 components of the gauge field here. And it's a quantum mechanical problem. You start from some system of just the scalar with half integer angular momenta. You add a particle with angular momentum 1 and spin 1, and then you know what the good quantum numbers are, namely the sum. And this time you do a mode expansion to diagonalize this problem here, inspired by the simple problem that we solved. So you expand on the scalar part on monocole spherical harmonics, and the vector part you expand on vector monopole spherical harmonics. So there's some combinations of spherical harmonics with spin 1 representations. So there are 3 constants here for a given value of j. And then you assume again that the radial part is given by some Bessel function with some index nu. And you ansatz into this equation up here. And then it's an eigenvalue equation, which give you possible values of nu, the index of the Bessel functions, and then these expansion coefficients here. And it all looks pretty complicated. It's full of 3J, 6J symbols and so on. But if you look at it carefully, then it turns out that the possible indices of the Bessel functions are very neat. Just these 3 possible values for a given value of the total angular momentum. And that's actually interesting to contrast it with the no scalar present, where you just have the spin 1 particle. You have only 3 values of this nu, of course, but they're not very pretty. They're actually irrational values, and you cannot write things in a nice enclosed form. But because of this to the scalar, then you get very pretty values coming out, and everything is and looks very pretty. And as I say, I think this simple spectrum is a manifestation of the underlying integrability. Yes. Yeah. So yeah, we had this before. We had the propagator for a simple scalar. Now we need the propagator for this scalar, which mixes with the gauge field. And again, it will have some part which tells the angular dependence, which is given by Jacobi polynomials. And this time it will have 3 different propagators appearing, because there were these 3 possible values for the index of the Bessel function, the nu from before. And again, it's a mode sum. It's an infinite sum over all half-integer values of j. But when you need to compute one-point functions for this complex field set, then you need a propagator for a combination of scalar fields, phi1 plus I phi 2, where phi1 is simple and 2 is complicated, and you need it at coinciding points. And that gives a lot of simplifications. First of all, you get a difference between 2 propagators. One is simple and one is complicated. So you need something we call G minus, which is the difference between these 2 propagators. And then for the one at coinciding points, so this is an operator with all the fields sticking out. Most of them you replace by their vefs, and then you make one contraction by one. And that propagator is a difference between 2 types of propagators. And when you try to compute it explicitly, and eventually we want to set the 2 endpoints of the propagator equal to each other, if you first make the identification of the angular coordinates, then already you have a really huge simplification. The big sum over angular momenta telescopes, and you are left only with 2 terms. So 2 ADS propagators, which correspond to 2 different mode numbers. And as you see, when the monopole charge goes to 0, then you don't get, because then both fields have the same standard 4-dimensional scalar. But if you send the 2 fields to coincide and you go to 4 dimensions, then the resulting effective propagator is simply non-singular and 1 over 8 squared. Which is extremely simple coming out of this long computation. And there's an interesting thing to note, namely that up here you can send q to 0 and you get 0, but limit does not commute with the limit down here where you send the points close to each other. Then you remain with this type here, with this term here. Okay, so that term is exactly what we need to compute that pole, which will be the simplest correction to the one-point function. So it gives me this factor here, and then times lambda over, I think it's 2. So all in all, at tadpole, simply give me this computation, and the tadpole will give me the simplest correction to the one. Okay. Yeah, and now I can actually easily find out what are the origin of these non-wrapping corrections that I listed in the beginning. So here is again this sum of non-wrapping corrections, which was finite at the order which was a length over 2. So you see the last part here with this coupling constant dependent, that's exactly the tadpole. And then this combinatorial factor here, it actually just in how many different ways you can insert n tadpole per operator. You can see it if you take your operator, you cut it open at some point, and then you're instructed to contract neighboring points, deciding what is easier to draw them like this. And you have to contract neighbors, need a large n limit to work out correctly. So this type of contract the first and the last point gives just this binomial factor, and then you get a similar factor if you contract the first and the last field. And you can convince yourself exactly what you do when you do the perturbative computation. So what we can conclude is that these non-wrapping corrections, they come exactly from contractions which only involve tadpoles. That is a little bit curious because there are potentially many other Feynman that would contribute. There are many Feynman diagrams with internal loops and internal basically infinitely many, but apparently they all cancel out and contributions from these types of diagrams, which you can describe them as diagrams with a varying number of leaves. And that's simply all. For some reason, all other terms disappear. As I already mentioned, you observe the same phenomenon in the 85 program system and also in the Gucker-Witten defects. So there's even no wrappings. Okay, so we've understood most coming from localization. So let me see what we have understood. Yes, we have obtained this new example of a defect CFT, which can be treated by localization and integrability, and which is of codimension 3. And we have completed its quantization, and of course we have a good check that it's correct, that it reproduces all these things from localization. And we've observed this intriguing structure of perturbation theory, of which we have now understood more or less half. Then it was all about protected operators, and I chose not to talk about the non-protected ones, but we can get them from integrability. At the lowest order, we have in the paper with Kostya a closed form for all one-point functions. Actually, by doing some kind of bootstrap integrability, also get them to higher loop orders, at least up to some dressing phase, and that was done by Gombo and Beinart. With this quantization, the scene is set for the full solution by integrability, where we can presumably determine this missing factor from the Beinart-Gombo paper, and then also the wrapping corrections. Yes, and that actually leads me to my conclusion. One of my conclusions is that monopoles are very fascinating, also in n=4. So what we really want to do in the future is to do these wrapping corrections. This was an everlasting problem from integrability. Of course, with the full quantization in place, we can extract, in principle, all other kinds of correlation functions we like, all kinds of conformal data, but to boundary couplings, 2-point transport coefficients, and in principle, get the conformal boundary program going. And finally, I got a little bit obsessed by monopoles. I think it would be interesting to study also in other dimensions and other. Okay, thank you very much for attention. They can simply not fix that dressing phase.
So hi everyone. Today, as Carlos was saying, I'm going to tell you about chaos in deformed SYK models. And this talk is based together with my postdoc, Saskia De Mulder, and my student, Osher Shoval, and with Damian Galant and Sam from King's College in London. So let me start with a bit of motivation. So why would I be in the first place in studying chaos in deformed SYK models? Well, the obvious motivation, there are two parts to this motivation. This part has to do with the quantum many-body systems that we would like to understand better. Some of these systems are chaotic, some of them are integrable, and in fact, even if, let's say, chaos in many-body quantum system is kind of a subject of debate, signatures proposed for defining that, and I will mainly focus on two of these signatures, which are the out-of-time ordered correlation functions and Krylov complexity, and I'll define everything. Part of the motivation comes, and I think that's common to many of us, from attempts to understand quantum gravity and the holographic correspondence. And in this context, SYK is famous because it's dual nearly anti-de Sitter 2 space-times. So in this sense, it provides some copic model of space-time. And so it's very natural whether small changes, different versions of SYK, understand this very, very specific type of duality and give us more rich space-times, and in particular, I'll come back to that at the end of my talk. Okay, so yeah. So after this slightly longish motivation, I'm going to start a bit of background about the SYK models and what do I mean exactly by talking about the of it. I'll introduce different signatures in quantum many-body systems, and then I will show you some results for signatures of chaos in these deformations of SYK, and come back to the gravitational motivations towards the end. All right, so the SYK model. So the SYK model is a model made out of n Majorana fermions. It's a disordered model, so it's not one model, it's an ensemble of theories where the Hamiltonian is constructed using random couplings, these J's, that are sampled from a Gaussian distribution, zero mean, and the specific variance, which is uniform. And typically, each term in the Hamiltonian contains Q fermions out of the n that are available. And this is very interesting because it's both in certain limit exactly solvable, also maximally chaotic, and I will say exactly what that means at low temperatures. It has a specific case, which is the case with two fermions in each interaction term, so basically like a fermion mass term, which is integrable. And from the condensed matter perspective, it's also very interesting because it's used to model strange metals, which are many-body quantum states with quasi-particles. All right, so I said that one of the reasons why this model is remarkable is that it's exactly solvable in certain limits. And in particular, I'm talking about the large n limit, so when I have many fermions. In that case, the partition function for the S can be written in terms of effective degrees of freedom, which are the bilinear fermions and the self-energy. And one can write for them an effective action, and this effective action is much more accessible than the model, the original model, since the original model is built from matrices exponentially with the size of the system, so that becomes unmanageable extremely quickly. And if I'm trying to solve equations of motion coming from an effective action of two functions, then I have to solve some integral differential equations, but in complete different order of magnitude of complex of being a complex system. A Occasion arises when I not only take the available number of fermions n to be very large, but also the number of fermions in each Hamiltonian term to be very large, with a specific ratio kept between these two quantities. And that's famous as scaled SYK, but I'm actually going to take first the number of large and then the number of fermions in each Hamiltonian term to be large. So that for those familiar with double scale, SYK is the limit of this lambda going to 0. But that's going to be rich enough to tell the story. Ah, sorry. All right. Another remarkable property of SYK is that at low temperatures, it's nearly conformal, and that means that at a fixed point where each one of the fermions has an effective conformal dimension of 1 over Q. Q was the number of fermions in each Hamiltonian term. So then essentially is given by a conformal action plus a correction, which is Schwarzian-like, built from the zero modes of the effective degrees of freedom of the previous action. In this limit, the model is maximally chaotic. So it attains the maximal limit of perturbation spreading. I'll say what that means in a second. All right. As I said at the beginning, there is a dual gravitational interpretation, JT gravity, which means gravity plus dilaton. The bulk theory is just a rigid ADS2, and so the dynamics effectively to the dynamics of the boundary mode. Yeah. All right. So then, knowing all that, raises an okay. It's nice to have rigid ADS2, but what more can we do? Can we have a little bit more rich gravitational background by playing a little bit with the SYK models? And the answer is yes, but it's not, because what you would like to do to get a slightly richer gravitational background is typically deform the interior of the model, like add something by R. But building relations of the SYK model is non-trivial. So the reason is the following. So what would you think would be the natural thing to build is, the obvious thing is, let's take go to the first fixed point, take two fermions, contract them together. Typically, one wants to also preserve the ON symmetry of the model, so psi I, psi I. That doesn't work because they're fermions, so that's 0. And then the next best thing is a time derivative, but that's already irrelevant because each time derivative adds one dimension, and the fermions already have a dimension around, so that's irrelevant. But the one thing that you can do is add SYK Hamiltonian disordered, another disordered contribution. So to take an SYK Hamiltonian with Q fermions and add to it another SYK Hamiltonian with Q tilde fermions. And that thing, as long as Q tilde is smaller than Q, is going to be, at least with a naive counting, relevant. And so it's going to be a deformation which becomes important in the infrared, and it's going to change the background in the interior. Right, okay. And it turns out that basically all the tricks that I told you about before, like taking the large n limit or taking the large q limit and all these things, are also relevant here. The very similar simplifications to the model with the deformation. So in particular, effective action in terms of bilinears can still be written, and effective motion for them can still be written. They are just changed a little bit by these red terms that you see on the slide. And furthermore, you could put large q limit, in this case both q and q tilde, with a fixed ratio between, and in that case the equations have an analytic solution. So all the simplifications persist. And that's it more or less. So I'm going to tell you in a second what I'm going to do with this model, but just to recap before I say what I want to study about this model, what I expect. So I expect, if I look at a Hamiltonian, which is an SYK Hamiltonian deformed by another SYK Hamiltonian with a different, smaller number of fermions, I expect that in the UV, when I go in the very fine details of the theory, I'm going to have that's true for the SYK as well. When I slightly zoom out, scale of the random coupling, this J tilde, I'm going to see the immediate phase where the Hamiltonian with Q fermions is going to dominate. And if I zoom out some more, assuming that really there is a separation, so assume the coefficient of the deformation is small, I'm going to see a deep infrared regime starts to fill the Hamiltonian with the Q tilde fermion. So I should see, I naively expect, is two regimes of maximally chaotic theories. And the question of this talk is going to be, I see that. How can I diagnose that along the flow, so by changing the temperature, I am able to see two regimes of nearly maximal chaos. And for that, I need to tell you how to diagnose chaos, how to define chaos. So for the, yeah, I don't know. I've had the chance to ever talk with a condensed matter physicist about quantum chaos. It's everyone thinks it's something else. So I'm stick with two definitions, and I will tell you the motivation for those definitions. So the first one requires having a semi-classical limit. So at large n, it makes no sense when I'm away from large n, and that's the idea of the out-of-time order correlation functions. And this draws from basically our classical idea, which is hypersensitivity to initial conditions. I change a little bit the inputs of my system. The final outcome changes a lot. In other words, nearby trajectories diverge, and they diverge exponentially. And the exponent, so you see dq of t by dq of 0, the exponent of some exponent, and that exponent is called the Lyapunov exponent, the famous butterfly effect. Now, if I'm in the semi-classical limit, then that deviation with respect to initial condition has a natural analog, since it can be written in terms of Poisson brackets. It's just analog. The quantum analog is the commutator. So that's something that would, in the semi-classical limit, collapse back to hypersensitivity on initial condition. And so basically what you would naively expect is that essentially commutators of two operators, one at time t, one at time 0, should diverge exponentially. There are a few ingredients to add to this if you want to do this in a quantum mechanical setup. First, one needs to take an expectation value within a certain state. That's usually taken to be state. And furthermore, often naively taking expectation value can have phase cancellations. So what people do is they take the square of that thing. And the square of that thing is essentially 4 point functions of 2 at time t, 2 operators at time 0 out of the time order, and that's the out of time order correlation. And that thing in chaos is expected to indeed behave with an exponential. So it's expected to have two terms that compete with each other, that can only be separated when there is a small parameter, say large n. And that's the behavior over there in the square. So it's a constant minus an exponential behavior. It's not quite, it's a related quantity to the one I not quite the same. And that's something that people compute. So they compute the expectation value of operator at time t, operator at time 0, and another time the operator at time t, another time at 0, and read from it the Lyapunov exponent. The famous bound on chaos by Maldacena, so it should be bounded in all physical systems pi over beta. That's maximal chaos. That's what I say. When I say maximal chaos, that's what I mean. And as I said, you need a semi-classical separation to the different terms, so to even define that quantity. The need to have a large n limit made people unhappy, so they look of chaos in systems that don't have a semi-classical limit. Led to defining this new guy. That's like last 4 years, like a very big surge of interest in this new signature, which is Krylov complexity. And the idea is essentially a new signature which estimates, tries to estimate if the system is chaotic by looking at the spread of a perturbation. So you take a system, you put in a perturbation, a specific location, and then you start evolving the system with the Hamiltonian. And you ask, how does this perturbation spread? And one way to estimate that is to notice that the spread or the operator evolved to time t can be constructed by a basis of operators and nested with the Hamiltonian. So the original operator, its commutation with the Hamiltonian, its commutation with the commutation of the Hamiltonian, and so on. And the idea is that the more the Hamiltonian you add, the more complicated is your operator. So what you really want to know, a weighted version of how many of these operators do I need, so that estimate how complicated the operator became at time t. So that's the quantity that you see. That's this ck of t, the Kirillov of complexity is essentially n is the number of the operator in this chain, times how much of it do I need to build my time-evolved operator. And that thing was conjectured to also behave in a quantum chaotic system with another lambda k, the Kirillov exponent. Okay, and as I said, the nice thing is that there is no need for large n in this approach, and it's much easier to compute. So this I didn't say, but somehow by manipulating a thermal two-point function of a theory and doing fancy things, one can get that without ever computing a four-point function. So it's a much easier thing to compute. All right. Few bounds were proven about this new exponent. It bounds above the Lyapunov exponent. It's always smaller than the bound of chaos. And in several cases, in particular in SYK, it's exactly equal to the Lyapunov exponent, which is kind of a magical thing. And that led people to think, maybe we can, not compute four-point functions are a mess. Let's just compute this Kirillov guy. As a way to measure chaos, we're going to see this exponential behavior, whether it's chaotic or maximally chaotic or whatever. And so that brings me back to my story. So now we wanted to use these two signatures if the flows SYK, if they are chaotic or not, if they have of chaos, which of the signatures can diagnose that. So the questions to answer are, what are these lambda L and lambda K in deformed SYK models? Are they equal to each other? And can they both diagnose chaos or chaos transitions? And everything I'm going to be at large n, of course, because if I need to compare one thing that is only defined, I can only do that. All right, so a few first results are expansions. So at n goes to infinity, q goes to infinity, that's the limit where the solutions are analytic. The values of the two exponents are in fact the same, and of course by all the bounds that I showed you earlier. But as soon as you go away, as soon as you have a finite number of terms in your a finite number of fermions in each Hamiltonian interaction, that's no longer true, and there is already a small deviation the two exponent, which is of order 1 over q and 1 over the temperature, and proportional to the temperature. But a much larger deviation can be seen when you start exploring this. So that's, I would say, one of the main plots. So here there are Hamiltonian with q fermions, Hamiltonian with q fermions, and q is taken to infinity. So there is, I do expect of nearly maximal chaos, and that's actually what you kind of see in the figure. So the figure has two lines. One is orange, that's the Kirillov exponent, and one is dashed black, and the exponent coming from the Otok, the Lyapunov exponent. And you see that, let's start with the Lyapunov exponent. So as I decrease the temperature, increase beta, as I flow to the infrared, I free, so with very small exponent. It's normalized so that maximal chaos is at 1. So then a region of near maximal chaos, then a transition, and then another region of nearly maximal chaos. But the interesting thing is that the Kirillov exponent doesn't see any of that. So we're not a very good signature of chaos, at least in this. But we do see, we do, by using the Otok, see these transitions. Good. So that's one thing. Sorry. And the next thing we wanted to do was to look at finite Q, so not infinite Q. The limit Q is not requires a bit of numerics. So for example, 6 fermions deformed by 2 fermions, or 6 by 4. That's very useful because you can have anything deformed by 2 fermions. You can have chaotic integrable transitions. And so these are a bit of details of the numerics to convince you that there is some work into it. So what to do is basically take the Schwinger-Dyson equations, which are those that give the linears, rewrite them in Fourier space using a spectral density, and then solve with some iterative procedure when one solves one equation in position space, then one in momentum space, and back and forth, to extract the two-point function in various continuations in Lorentzian time. From the moments of the two-point functions, which are essentially related to the different amplitudes of the operator in the Krylov basis that I showed earlier, we can get the Krylov exponent. Then then the 4-point function comes from some kernel equation that one diagonalizes using big matrices. So that's kind of a heavy numerical procedure, especially hard at low temperatures. Is involved, plus a deformation with a small parameter where in term there are 2 fermions involved. And as I said earlier, the 6 fermion is expected to be chaotic. The 2 fermions, on the other hand, is expected to be integrable. So what one expects is to see a developing of chaos and then back integrability. And indeed, that's what you see in the figure from the dashed purple line, which is the Lyapunov guy, not extremely visible, I think, but and on the other hand, the one just doesn't see anything, keeps going up, nothing special happened. So we see that also in this example, the Lyapunov exponent sees the transition, while Krylov exponents don't seem to be able to diagnose of this type of flows. There is only one case for some hint of possibly Krylov being able to diagnose something, and that's the case where one takes infinitely many fermions, so that's Q goes to infinity limit, and deforms by fermions. It's not that the Krylov exponent dives back to an integrable regime, but just at some point the behavior stops being exponential, and so it's like more or less around the same point where the transition happens for the Lyapunov exponent. Also, the Krylov exponent does something weird. All right, so I'm gonna do a small recap of the, and then I'll say a few words about gravity. So we saw deviations between the two type of exponents meant to diagnose chaos. These are the Krylov Lyapunov exponent coming from the OTOC already for the single SYK. For most cases of flows, of flow SYKs, the Krylov provide a good diagnostic of chaos transitions along RG flows. And in all examples, the Krylov exponent seemed, when it could be defined, grow monotonically. So that's maybe a conjecture for quantum systems. And now let me go back to talk about the relation to space-time. So we know that K, at least in the low energy limit, is dual to ADS2 space-time, that I said at the beginning. Now, the dual space-time to deform the SYK is also rather well understood. And it's actually dual to an infrared deformation, where one takes an ADS space-time and roughly, not in an abrupt way, a continuous way, changes its interior to be another ADS2 space-time with another cosmological constant. And this relation is rather well understood both from the point of view of the thermodynamics of these space-times and from the point of view of the Schwarzian action. So the different calculations were made to do the exact matching to understand exactly what dilaton potential one would need in JT to exactly get the model to these SYK flows. in 2D, there is another interesting fact, which is very special to 2D, so that doesn't work this way in higher D, is that one can also, instead of slicing a small chunk of the interior ADS and replacing it by another cosmological constant, is to throw away this interior and replace it with the chunk of de Sitter space. So there are constructions. They're possible in 2D in a much more obvious way than in higher D, is because of some focusing theorems that are not limiting because there is no spatial sphere. These geometries have been constructed. So geometries with an interior de Sitter with the available and an exterior ADS in 2 dimensions. And that's very appealing is that many people have tried over the years to talk about lithography, and one of the main roadblocks are the fact that we don't have a time-like boundary on which to put the field. But of course, once you put an interior de Sitter, but the exterior is still ADS, this exterior still has an asymptotic boundary where the field theory can live. And so it really does beg the question of whether these models are described in terms of some type of flow SYK. So it's a change of the interior of a gravity setup with where the exterior looks like ADS2, so probably an SYK, and some interior deformation that creates a de Sitter. And it's not exactly those flows that I was telling you, but we have some hints for what could be the dual theory. And the hints come from, so how do we try to look for a dual theory? In these cases is to begin by looking at some of the properties of the background. So test, I don't know, the thermodynamics, test how we react to shock waves, test properties of the gravity background, and ask what properties do you expect from the would-be dual field theory of this model. And some things has been done, but most interesting is the fact that when one studies thermodynamics in those de Sitter bubble style geometry, one finds actually the dynamics would have matched a flow SYK with a complex coupling. So HQ plus IS HQ tilde. Okay, doesn't mean that we know what that means, right? Because we obviously like to work with Hermitian Hamiltonians. But non-Hermitian Hamiltonians do appear in the context of open quantum, in the Lindblad equation and so on. So, so that might be a hint to think that de Sitter bubbles are dual to open quantum systems because they can evaporate behind the cosmological horizon and just go to Scri plus. So, yeah, so that's just a hint towards perhaps some type of flow with some type of open quantum system could be dual to these de Sitter bubbles, but the answer is that we don't know. That it's much less understood than just the flow, but this is just to give motivation. That could be interesting. A lot of work has been done about chaos in systems, so it would be interesting to make this connection much more precise. Yeah, I think that's it, more or less. That's what I wanted to do. I think so. The Lyapunov exponent is encoded in the reaction of the geometry to shock waves, so that you can compute. And yeah, well, actually, I had some words on the slide that says that it oscillates in these de Sitter bubbles, so it's very different from an exponential that you see in other contexts. So you really different type of behavior. The complexity. So very recently there were works by, starting by Sonner and Rabinovici, and then a lot of works by Vijay, Balasubramanian, recently that found a precise connection between this Krylov complexity and the volume. Again, everything in the context of two-dimensional gravity and the volume of the wormhole. So you know that thing that was advertised for a long time to be related to circuit complexity, but they were able to a very precise relation between the volume of the wormhole in two-dimensional. Well, that's a geodesic, and the definition of Krylov complexity, and they understand very well what is this, what is the decomposition, like all the ingredients that come into the definition. They understand well how they match between the sites. So yeah, possibly if you do this matching in a smart way, maybe you can use that to understand. Yeah, I don't know. The answer is I don't know. But maybe I think you should not be extremely surprised, because it was already to begin with very suspicious that something that you can compute really from the two-point function would encode something that you have to do so much work from the out-of-time order correlation function. So there was something to begin with a bit unnatural about this proposal, and I think many people were kind of suspicious about it. But now it's a very clear example where you can see that doesn't track chaos transitions. I'm not sure how to, yeah, what's the gravitational version of that statement? It's a good question.
Might be naive, but I'm wondering which are the criteria that indicate whether type flow would lead to intelligence. Are there any criteria for the flow?
Yeah, so I mean, I think one of the things we want in the context of chaos, the one that was studied in this talk, is so in the de Sitter bubbles, we know that whatever the gravitational quantity with the shock waves that is dual to the OTOC has fluctuations. So instead of being, it fluctuates. So that's one of the properties that you would want to reproduce in a theory, and the exact pattern of fluctuations you would like to reproduce in a theory. It would be the dual of that thing. But thermodynamics, the specific heat, the various things, anything that you can compute in the gravity, of course. To understand what it means, I mean, a little bit, I mean, in a sense that it's a thing, like you need to understand what it means to have a non-Hermitian Hamiltonian, right? You cannot just plug it into your formalism and go ahead and see what comes out. Yeah. So they have formalism for describing certain types of open quantum system, like memoryless, where the buff. So a buff, you integrate out the buff. The buff is not changing too much, not too quickly, and in this formalism, the way that density changes as a function of time involves not only but also involves a non-Hermitian Hamiltonian and other things, two ends of the bath. And people did try to generalize some of the signatures. There's not like a very deep understanding yet, but yeah, like you said, there's like this long list of people that try to do signatures of chaos in open quantum system. Usually they don't, they postulate a form for this evolution of the density matrix, thinking exactly where it's coming from. I don't know, I mean, another thing that you could think morally is that you have now when you think about the de Sitter bubbles, you have actually two boundaries. So you have a boundary of ADS, but you also have Scribe plus, which is a boundary of de Sitter, which is Euclidean. I mean, it's not time-like. And maybe one of the SYK describes the ADS part, and one of the SYKs describe this additional part, and what does it mean in a kind of quantum mechanical context? I don't know yet. But they are like, kind of, it would be nice, right? I mean. Well, no, yeah. I don't know. Yeah, yes, yeah. I know that indeed there are. So there are some very specific. I don't know what PT would mean. Okay, let me say. There is some class of Hamiltonians that are non-Hermitian but have real eigenvalues in systems that have PT symmetry. But here it's not clear what that would mean. So the examples are like, harmonic oscillator-like. It's not exactly clear what that would mean here because there is no space. It's a quantum mechanics with many fermions, but they don't actually sit on a chain. So there is no space. It's not very clear what it means to do a parity transformation. Yeah, maybe. Yeah. No, I think I don't have a good answer for that. Not a definitive answer.
περισσότερες, στη πλειοψηφία των ιστοριών δεν η ψηφιακή αφήγηση είναι αρκετά αποτελεσματική σε αυτό το θέμα, καθώς οι γυναίκες παρουσιάζουν τις αφηγήσεις τους με τη δικιά τους φωνή, γεγονός το οποίο συμβάλλει στη συλλογική αφύπνιση. Η χρήση οπτικοακουστικών στοιχείων ενισχύει την επίδραση των αφηγήσεων και παρατηρήθηκε ότι στο σεμινάριο που έγινε για να δημιουργηθούν αυτές, οι γυναίκες συνειδητοποίησαν ότι έχουν κοινές εμπειρίες από από τη χρήση των μέσων μαζικής μεταφοράς και συνέβαλε στην αλληλεγγύη μεταξύ τους. Το σημαντικό που βγαίνει λοιπόν από αυτή την έρευνα είναι ότι παρόλο που σήμερα, στο 2025, σε μια κοινωνία που υπάρχει ισότητα των φύλων, οι έμφυλες διακρίσεις είναι έντονες και περιορίζουν καθημερινά τις γυναίκες και η έρευνα επιβεβαιώνει και άλλες παρόμοιες έρευνες που έχουν γίνει, όπως του ΕΚΕ που έγινε το 2020, καταπολέμηση των πολλαπλών διακρίσεων στην Ελλάδα, όπου καταγράφει την εκτεταμένη διάσταση των διακρίσεων στο δημόσιο χώρο. Αυτά είχα να σας πω. Τώρα θα ήθελα να σας δείξω και δύο αφηγήσεις, προσπαθήσω να τις κάνω κοινοποίηση.
Πάρα πολύ. Σας παρακαλώ πάρα πολύ. Απλά συνδέθηκα στο διάλειμμα, θα φύγω μόλις...
εντάξει,
σας παρακαλώ, είμαι από το διπλανό συνέδριο. Χίλια συγγνώμη, δεν έκανα τίποτα, μόνο έβαλα αυτό.
Τι χρειάζεται να κάνεις?
Παρακολουθώ μια διπλωματική που έπρεπε να είμαι μέσα και...
Απλώς μόνο επειδή είναι καταγράφεται τέτοιο...
Καταγράφεται η διπλωματική της κοπέλας.
Καταγράφει όλο το αμφιθέατρο. Μέχρι τις 1:30 θα καταγράφεται.
Εντάξει. 2 λεπτά θα καθίσω ακόμα και θα φύγω. Δεν πειράζει τώρα, εντάξει. Βγάλτε το σας παρακαλώ από το μέσα.
Αλλά καλό θα ήταν να μας το είχατε πει αυτό το μοντέλο.
Εννοείται. Απλά δεν βρήκα κανέναν και ήμουν σαν τρελή. Ήρθα αρχικά σε συνέντευξη. Ευχαριστώ.
Είναι ο κώδικας. Όπως λένε τα παιδιά, να παίζει το βίντεο. Παίζει όχι. Αν δεν παίζει την οθόνη σου, δεν πειράζει.
Όχι, στην οθόνη μου παίζει, ναι. Όπως και τώρα. Ενώ έχω κάνει διαπειρασμό, δείχνει ένα ελληνικό εικόνα. Τη βλέπετε? Δεν ξέρω, τις έχω κάνει κοινοποίηση στο Drive τις ιστορίες. Υπάρχει περίπτωση να κάποιος διαβιβασμός από εκεί. Θέλεις να μου στείλεις το mail? και δώστε μου, συγχωρέστε με.
Είναι παλιό, είναι πασπάλιο, είναι πιο παλιό. Έχει κάνει έτσι. Αλλά νομίζω το κάνει. Εδώ δεν είναι.
Είναι κάποιοι νόμοι που πάνω που έγιναν έτσι, δεν μου φαίνονται.
Άλλο αυτό, άλλο στη φόρμα, όταν ήταν στη φόρμα. Γιατί μου λέει δεν είναι. Οκ. Εδώ πέρα everything είναι test. Λοιπόν, εδώ είσαι.
Ναι, τέλεια. Έβαλα και φωτογραφία της Αθήνας.
Α, εδώ. Α, πολύ ωραία. No, 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 not là. No, no, no. Tu ho cercato io. No, 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 no. No, but they go through Russia, which is still, I think, 1 or 2 hours. They do. I mean, Lufthansa goes overnight. So long, probably something like
Okay, so let's continue morning session. So the next speaker is Ellie Pomoni, who's going to tell us about hidden symmetries of 14 equals 2 gauge theories. Please, Ellie.
Thank you very much. And let me begin by thanking the organizers. It's always a pleasure to come back. Yes. And sorry I didn't come last night. It was too much happiness. This work. So this is what I will explain this paper. It is a bit esoteric for if you are not an integrable person, but I have made and explain it. So don't worry, just stay with me. Yes. Yes. So, yes, so n equal to 4 is integrable in the planar limit. If you are not integrable, remember that we are only in the planar, yes? This is only large n, yes? And yes, using integrability, the spectral problem is solved, and you can use integrability to compute basically your favorite thing. This is amazing. And because I know that there are some students, the next 2 slides are only for them. So if you are super expert, you can chill. So Sibylle had in her talk the 3 things, the n equal to 4 super Yang-Mills, ADS5 cross S5, and the spin chain. I will only have 2 for this talk. So what do we do? The important thing is that there is a one-to-one map, single trace operators to spin chain states. So this is a nice spin chain state, and here is a Feynman diagram, and you can see the insertion of the operator as a spin chain. So in some sense, the picture is enough. I will say a few for the students. So the fields in n equal to 4 super Yang-Mills are a representation of the color group, and because of that, it's important the order in which you put the fields when you make the operators. The way you should think is that operators are words, and every field in there is a letter. Yes? So, and what I said that they are non-abelian, the order matters. So what we do is we just did our letters, and the map is one-to-one. The moment we also impose that the spin chain has periodic boundary conditions, but not also translational invariance in order to capture the property of the trace. Yes? So that's the map, and that's a good exact map. To make things very simple for this talk, I will only concentrate on the possible sector, subsector of things that I can look at, which is called the sector, which for n equal to 4 super Yang-Mills is take 2 of the 3 complex scalars of the theory. They are rotated by SU2R symmetry. Here they want to spin up and down, and this SU2 is the symmetry of the spin. And most probably you studied this in your statistical mechanics course. And correspondence, what we need to know is that the spectrum of operators is mapped to the energies of the spin chains. So in order to calculate that, we only need to calculate energies of the spin chain. So on the gauge theory side, with rotation operator, we have calculating Feynman diagrams, and this renormalization is mapped, is known by a Hamiltonian acts on the spin chain. So the name of the game is to diagonalize this Hamiltonian. And this captures all these Feynman diagrams. And as an example for this SU2 sector, it so happens that after a concrete Feynman diagram calculation, you discover that this Hamiltonian is an XXX Hamiltonian with an integrable model, and everyone is very happy. Yes? So this is, in 2 slides for the students, what is the integrability for n equal to 4, at least the part I care about. Of course, there is way more and beautiful, and yeah. So now, great, n equal to 4 super Yang-Mills is integrable, but you know, we are supposed to be physicists and we want to go to QCD eventually. Not quite yet, but the important question to answer is what happens for gauge theories as I reduce supersymmetry. Yes, this is a very important, honest question that we need to answer. So the next step after n equal to 4 super Yang-Mills is n equal to 2 theories. And they have a, first of all, if you ask generically what is the landscape of n equal to 2 theories, it's basically vast and unknown, I would say. However, if you care about theories that have a Lagrangian description, Vasilis yesterday already said the word Lagrangian or non-Lagrangian. So only Lagrangian we know how to do integrability. Actually, verification. So we know all the theories that are n equal to superconformal and have a Lagrangian description. And you can just look at them. And most of them are made by orbifolding n equal to 4 super Yang-Mills. When I say the word orbifold, I have also orientifold here, so they are the same, more or less. Yeah? And originally deforming along the conformal manifold. So that's the name of the game. Orbifold marginal deformation. And for these things, we know what the gravity dual is, so we can also have an ADS description for them. This is very important. And basically all you do is you take the n equal to 4 paradigm, you orbifold, and then there is a B field that you need to play with, and it's your marginal deformation. You play with the B field. Yes.
Do you have any, this is the Bernardo solution?
Yes, absolutely. It's in my first activity with Leonardo, the Veneziano limit. Yes. Yes, yes, yes. So the supergravity doesn't care about the B field because only H appears, and for us H is equal to 0.
How can the
Yes.
spectrum of the string then depend on it?
Very good. String theory now becomes important. Supergravity is too simple. So the twisted states know about this. That's how it goes. Very good, very good. Yes. So, and what is also important is from the very beginning of the integrability, people discovered that at the orbifold point, which is a specific of the couplings, where all the couplings are equal, these theories are integrable. So very naively, all we need to do in this life to go beyond is we need to understand what the marginal deformation does to the spin chain. Simple, but yeah, let's go for it, yes? Let's try to understand, yes?
Before you go there, what about the limits that you do not obtain from orbifold?
Yeah, they are a little bit strange, and maybe you need to start from F theory to understand them. Some special crazy G2 blah blah. When I understand type 2B, I will go to F theory.
But are there examples that are understood, or is it not understood?
What do you understand? So we know how to do string theory constructions. I think more or less, I mean, I wouldn't sign now a paper, but for more or less all, we know what is the gravity dual. You may have to do F theory to do that. Now integrability and all of these things, not even forget. Yeah. No, I think gravity dual to the right F theory person, they will tell you the most strange one. Yeah. Let's we can go. Yeah. Good. Okay, maybe I will think just because you said Weil. So I will just say one thing. There are theories, I will say this later, but I say it already. There are theories like super QCD n equal to QD. What I tell you now, and you can ask me after why L is you should never study it by itself because this is too hard. Because dual is a non-critical string, blah, blah, blah. You should always study an orbifold of which you can obtain this super QCD as a limit. Yes, so I just say that for now. Yeah. Great. So on the integrable model side, and here I want to insist and to try to brainwash several friends. Yes. So when you take a class in integrable models, they tell you there is rational, trigonometric, and elliptic. They teach you amazing things about the first two things, but then they start not telling you enough. And first of all, nobody even tells you that there are hyperelliptic examples. Find the strange papers by yourself. Yes? And so now let me stress something. So I already, for example, the XXX spin chain has SU2 symmetry. So when people started in the old times, they started, for example, XXZ, and naively yourself, you naively say, oh, there is only U1. No, if you really do your calculations and you study, you discover that there is a bigger thing. There is an SU2. It's just not a Lie group. It's a quantum group. And the same thing, and even more is here. Naively, you think that the XYZ model doesn't have a symmetry. However, it has an elliptic version of SU2. And actually, it's even very important how you choose your base because there are different classifications of elliptic groups. So actually here, I would even say that there is a vast unexplored arena to play with. And also what is super bad is that the mathematicians and the physicists have not talking at some point. And they know things that they don't know and the other way around. So even bridging this gap is like an important homework to do. Okay, now let's go back to theory. So we know n equal to 4 super Young-Mills has SU4R symmetry, n equal to 2 has SU2 cross U1, and n equal to 1 has only U1. But then you start studying spin chains and you start collecting evidence that something is happening. So already the beta deformed n equal to 1 is mentioned, and this has a quantum deformed SU4R symmetry. Whether you like it or not, it's there. The most general to one marginal deformation that you can do has a 2-parameter deformation U4. So it's not as little as we thought. For the orbifolds, nobody talks about it, but if you read at the papers where they do the integrability stuff, they actually use U4, which why they do it, they shouldn't have done that. Yes? Never argue that an SU4 is there. SU4 is broken. And anyway, we had a very experimental paper where we started discovering that even away from the orbifold point, there is some type of deformation. And in this talk, in some sense, I want to really go, what is that? Now, message, because I already said at the beginning, naively, we only need to understand the imaginations. So from all the examples that we know, of course, this is not a theorem. For examples, this is what you get, is that marginal deformations on the gauge theory side, it maps to quantum deformations of the symmetry algebra, yes. Yes, you have a bigger, this is the naive, no, this is. Let's continue. SUSY algebra is for the beta deformed. The more the examples go down, it gets harder. But yes, that's where I am going in this life. Yes. So I think this is the important message that I want to, like, as far as we know, marginal deformations, they correspond to quantum deformation of SU4. By the way, all of the theories that we know how to study with integrability, all of them, they are a very close daughter to n equal to 4. So you can say it's an accident that this works so nicely, but anyway, that's what we have. And now what I want to really understand is what is the effect of the orbifolding and the spin chain. Yes? So let's do this. So this will be my prime example. Like, do the simplest possible n equal to 2 theory that you obtain as an orb and then marginal deformation. Okay, in the 10D, in the type 2B strings, you do this orbifold. In the gauge theory side, this is not enough. You need to remember that there are Champatton labels, so you also need to do the orbifold at the color indices of your and this is what happens in the end of the orbifolding procedure. Maybe just stress, the difference with n equal to 4 is that you have fields in the adjoint representation of the one color group and the other, but you also have bifundamentals. And this makes all the difference when it comes to integrability. Yes? This theory is enough to understand all the novel features that I want to understand. And what I try to say for the is super QCD, you should never try to understand it alone. You should do it as a limit of this theory. Now we start. So n equal to 4 super Yang-Mills is very nice because all the fields are in the adjoint representation. The superconductor algebra has a unique singleton representation. So the way Hilbert space is like crossing, putting however you like the fields on your speed chain, and you win. Now, the moment you go down to n equal to 2, generically, and there is no way out, you have to deal with this in this life, is that there are ultra-short representations of this algebra. One is built upon the vector multiplet, and one is built upon the higher multiplet. And the vector is always in the adjoint, and the hyper is fundamental. That's extremely important. Now what happens? You cannot just put the fields, the however you like in the word, because if you want to be in the large n limit, you always contract, and I have chosen my conventions so that you can immediately see how you act. So these are the color indices. You have to have a 2, follow it by a 2. This is not allowed. This would be sort of making a double trace operator if you do that. So the fact that not goes has been the biggest contamination, at least of my thought, but I think of any person that has tried to think about this problem. And now I have 2 ways to think about it, which I think are fantastic. So the one is a more physicsy way, but that's already something that people don't think every day. You need to think about a so-called dynamical spin chain. So what is the simplest way to think about what is this word? And this is not the Bizet dynamical for the integrable people, it's some other dynamical. So begin with an n equal to 4 mother operator. You should always think about sons and daughters, yes? And after the orbifold, you always get, after following the projection that I try to explain here, you get 2 operators. And as long as you specify the very first index, you know the rest follows. So this is what is dynamical about it, like when you solve a differential equation, you have a condition and then you solve. That's what's dynamical about it. So that's one way to think about it, and it's a very good way. But actually, in this paper that I'm describing now, we found a better way, and this is very important because if you ever want to make contact with the mathematical literature, you have to follow the way they think. And the modern mathematicians think in category theory. And the simplest object they have is called groupoid. But we know what is a path groupoid. We don't need to learn math. It's basically take your quiver and follow the arrows. That's a path groupoid. So the way to understand Hilbert space of spin chains is through this path groupoid. Follow the arrow. And this captures clearly, obviously for us, the correct Hilbert space. But it's another mathematical object. Now, there is not only the path groupoid which describes the Hilbert space. There is another groupoid that I will now try to explain. Explains to you why this SU4 is there. It's not a Lie algebra. SU4 is something that I will call the R-symmetry algebroid. Let's go for it. So, what do we learn in school? We learn, we have 2 fields, the tablet of SU2. This is good for n equal to 4, no problem. Now, for n equal to 2 theories after the orbifold, and this is what you learn when you take the standard symmetry class, naively you would put these guys together in one doublet, but that's not allowed because you are never allowed to put apples and oranges. So this is in the adjoint, this is the bifundamental, they don't belong together. So I need to make a new construction which will take into account, and that's precisely by abandoning the Lie algebra and going to a Lie algebroid. By the way, I am not going to be careful in this talk what is groupoid algebroid. I'm thinking if you group Lie algebra, you do the same and you are fine. Yeah? Now, what is happening? So for normal SU2 Lie groups, we have a raising and a lowering operator that will go up and down with your spins or your 2 fields. When you have lost this guy, you can say, let's start, like play stupid, it's ways to be stupid, and just postulate generators that do the same thing. Yeah? Clearly, operators, they are not just normal Lie algebra operators. They also know about the color, the representations of the color group, or better, they know about the Z2 of the orbifold. Now, this is, if you want to know what is algebroid, here you go. I mean, with the next few slides. So, at the level of single words, and I will tell you later what to do with more letters, all you need to do is to say, yes, my 4 different fields, they don't live in the vector. So I have a set of 4 different types of vector spaces. And I have these actions, so the arrows, so the action of the generators, of the algebroid. That's what it is. And in our case, because we are doing a Z2 orbifold, but you can clearly imagine how to generalize this very easily, there is another operation that takes things from up here to down here. It changes the index 1 to 2, and here the same. So this takes into account the orbifold. So I am now defining something that knows about the SU2, but it also knows about the Z2. And the set on which it acts is 4 different elements. If you know category theory, this is a small category, but forget about it. Now, one letter was too easy. Now the real deal comes the moment you want to have at least 2 letters. N equal to 4 super Young-Mills with this nice SU2R symmetry. We do how we learn when we add spins in quantum mechanics. This is the product, the way to put 2 sides together. You either act on the one or the other with no factors, no nothing. And that's how you build from a up-up spin and up and down symmetrized. So this is part of the triplet of SU2, yeah? Now you naively find some sigmas. You want to do the same, yes? So you go this naive and you act and you get foul, not allowed. So this color contraction is not allowed. Now it becomes very that we are in this algebroid picture and we have a new friend, the gamma, the guy that tells us how to go up and down. So if you realize your coproduct by adding this baby, and this is not some crazy thing that I wrote, this exists in math, it's called, anyway, I'm not gonna tell crazy names. So you take this, you act, and it's allowed. Yes? And you can continue, you can choose however many letters your word. Whenever you had a broken generator that would make a mess, you put gammas on the, if you will put things on the right or on the left is a convention, but I have chosen one and right. So you put gammas all here, and this guy acts properly, and it raises you up and down, and you can make all your representation. It's beautiful. Here is the definition. So it acts by changing the color from 1 to 2. Yes? So it's the non-trivial element of Z2 that squares to 1. And yeah, here the same. So this is what this is. And these generators now, since you can say that they obey like the SU2 algebra, of course this is not the SU2 algebra, because you need to have also all of this decoration indices that know about the color. And I am writing this, you can take this and do another orbifold now, this equation. Yes? Yes. So there is a paper by Diagraph that does this for minimal models. More after the talk. Yes. And then you can very clearly embed this construction. Opala. You can embed this construction as U4R symmetry. I am not going to bother you now with the group theory, but you can do it. It's the same thing. This is what is now the groupoid or the algebroid. So you have, for any length now, that's why I call it V. You can have open strings that they end in the same brain, open strings they end in the others, and so on. So 4 of them, and you have all the possible actions of all the different broken or unbroken generators. Unbroken generators, you don't mess with the coproduct. You keep it how we learn in the economics. Broken, you put your gammas. And then you can check they obey SU4, of course, with this decoration. Now, if this was it, I would not be giving a talk. What we will do now is the Lagrangian, and we will show that it's invariant under this strange thing. And I only know how to do this in the large N because I need to have this words making task. Yeah? So, first of all, trace operators are nice, but they have this periodicity thing. And usually when you do all of this more integrable stuff, you want to just act. If you have a nearest neighbor Hamiltonian, you want to act on two sides to ignore the rest. So usually you cut open the chains and you think about open chains. So I'm going to do this. You don't have to do this. And maybe this is something that I am constantly debating with myself. Maybe it makes life harder to always cut. Because in gauge theory, this makes gauge non-invariant operators. But anyway, I will cut. And encryption for how to cut when you have an operator with a trace, and it's this cyclic prescription. Yes, so that's how I cut. Okay, the one I'll drop in the next slides. And this will be enough to show you Lagrangian is invariant under this SU4 Z2 algebroid. So let's do it. And to not kill you, I will only show you how to do the superpotential, which is the most non-trivial thing you have to do. Everything else is easy. So this is my superpotential, first at the orbifold point, where the two couplings are equal. I cut it first by doing what I said before. And I pull out the 1 over G because who cares about it? In fact, this is just an example with a sigma plus. And I made also colors. Okay, they're not all of them super visible, but you get a cancellation. So this guy that was not supposed to be there gives a 0 when I act on my superpotential. You can do the same thing for the Kähler part, or you can torture. I tortured my PhD student by making him go also to components and check everything in components. And in components, it's harder because you have the scalar potential, which is 4 sites. So clearly, there's more to check. So, but you can go through all the pain, and you can test all of it, and you get that the Lagrangian is invariant. And if you do not open chain language that I'm talking about now, because the Lagrangian is a trace, you are doing this in the equations of motion. Yes? Great. So now we have shown that the orbifold is good and they have SU4, because not they have an SU4 Lie. They have an SU4 Lie algebroid based on the Z2. That's the correct way to think about them. Yes, the large limit plays a role in the thinking of things about like the spin chain language. No, but no. What I am doing is very important. I have sites that I can name 1, 2, 3, and I can put my fields on them and find a coproduct. So this type of thing that I am defining, this type of things, if there is no spin chain, it doesn't exist. So the independent statement is in Zen limit, when you are allowed to use this machinery, I can check it's invariant. That's the only statement. Yes, if you wish, I haven't checked because I'm not allowed even to think about checking them, is the double trace, guys. Naively in the superpotential, there is no double trace. To components, there are also double traces. And if you knew to write this formalism, you would also check that. Yeah. What does it mean? Basically, yes. What is not known is this. I mean, maybe Charlotte has worked. So you tried to do it, and it was. I don't know. Like, yeah, I really don't know. Maybe we can talk after. But I really don't know how to go beyond this formalism. So, good, we checked the invariance at the orbifold point. Now we want to check it away from the orbifold point. And in order to do that, I need to Good, here we are. So we want to go away from the orbit. I define kappa as the ratio of two couplings. And I am going to show you that the deformation is captured by a Drinfeld-like twist. And I call it Drinfeld-like because I don't understand the mathematicians that they talk about groupoids. I only understand the simple ones. So it's something like Drinfeld, but I don't know if all the... someone needs to make sure that it's all the yeah, anyway, it doesn't matter. It's what it is. And where do you get this twist? This guy, you get it by at the F and the D terms. So this is the F term without the marginal deformation. This is one, I just show one of them, yeah? And you really want to have, now that you have this marginal deformation, so if you calculate an operator at the spin chain level that does this job. And this we had already hinted in the previous paper. Great. I want to give a little bit of intuition because this is very important. That's the only string theory slide. So first of all, the F terms, if you forget about this, what they capture is the planes that are transverse to this when I'm looking at the scalars. Yes, this is the F and the D terms, this is what they do for you. So when kappa is equal to 0, they show you that there is an SO6 symmetry and everything is nice. And once you have this, kappas or whatever other deformation, this is the same for the beta deformed, for everything, it basically tells you that the transverse directions to these three branes are somehow deformed, squashed. But this we know. And we know since a very, very, very long time. So what this guy said is that once there is a B field that is transverse to the D3 brane, precisely what we have, the open strings, which are these guys, they see non-commutative geometry. And in the spin chain language, it's basically what we call a quantum plane. Important.
Again, so if I take these deformed background away from the orbital point, like it's the Green-Schwarz action for closed strings.
Nobody has written this yet.
Right, that was, I guess, my question.
Nobody has written this yet.
But I thought you said that the background is known, so what's the...
The background is a geometry. The background is not a Green-Schwarz action. Who cares the specific? The background is a metric, a B field, blah, blah, blah. And the background is given by string theory.
And that is known or not known?
It's known.
As to what is the problem there?
The problem is that someone, so from the string theory side, what is not done yet, I'm trying to convince people, is that we need to write down the Green-Schwarz action and calculate. Yes, it is written, but then you need to calculate. Let's not, we are really...
More general.
Yes.
If this is the only deformation that you have,
Yes.
I don't see how closed strings would couple.
Yes, because you are used to untwisted models, and twisted models have twisted strings, and twisted strings directly couple to the B field. That's how they couple. And if you do RNS formally, you can directly show that to make sure you have Walsh-Its supersymmetry, you basically change boundary condition. This is a calculation that you can do that I know how to do, and you can put the B field in the way you define your boundary conditions. So that's how it works. But yes, we need to, I commit to bring this in a form that the integrability people like, and they can take it and do whatever they want with it. Yet. Good, now we stay to the spin chain again. And we define our twist the way I said. When you have this mathematical object, it's the same like in your talk. That's how you define now a deformed coproduct, the deformed way these generators act. There is here a kappa, this is a marginal deformation, to some operator S. The operator S is the operator that asks the field, what is your first index? And it gives only 1 and -1 depending on what the first index is. And it commutes with this way. So we know everything. And now we do the same again. Here is the superpotential with G1 not equal to each other. Open up. There is something here in blue. I try to put color so that you can follow with your eyes. The coproduct. This is the same calculation as before. Kappas cancel. And then you get 0 the same way. That's how it works. And Kähler, the same. Ah, very nice. Good. So I have shown up to now that if you use the spin chain formalism and you define your coproduct I did, you can show that the Lagrangian is invariant under this symmetry. Yes, this is the equivalent for the integrable people of the Bizert papers showing that, when he wanted to show the Youngian. So I just showed the 4 there, but as in this groupoid sense. So that's done. Now, that's not just that. You can also go ahead and study now the spectrum. At this moment, I don't care about energies, calculating energies. But what I care is about representation theory of this groupoid. What is that? So what is that I can make representations of this algebraic structure. And this is how we do it. First, I start with the simplest possible SU2. And I start, you can do at any length, no fear, no problem. Spin up, spin down, acting with this coproduct. You can go up and down, and you can make this multiplet completely. This you are not supposed to be doing. Yes, nobody should allow this. Only you can do this. You get sprinkled kappas everywhere in place. And these kappas are the correct kappas that when I was a student and Leonardo made me calculate all the Feynman diagrams, is the same kappas. And this is a highly non-trivial test that this thing works. Yes? So this agrees with either you can say direct diagonalization of the Hamiltonian or Feynman diagrams. And also for the people that care about n equal to 2 theories in general, this multiplet now has Higgs branch type of operators, Coulomb branch type of operators, and mixed branch operators, all in one multiplet. So this is not important only for the integrability business. This should eventually show up when we learn to do BPS counting, all the Nekrasov partition functions, all of this should know about these things. So this implies a relation between Schur and Coulomb branch index. Yeah, I don't know. So there's a lot. Just only in the infinite, but still. So there is like a tone of modern developments that they should know about. The chiral algebras should know about the chiral ring of the tone.
So this is for a specific multiplet, right?
Yes. Yes. Yes.
You give me any multiplet, so I get any multiplet in the spectrum?
Yes. Wait. You embed everything in the SU4. There's a difficulty there, and this makes things. I don't talk about it in the correct way to phrase the computer. Vasilis yesterday in the talk, he was saying how you should talk to the AI so that in a way that it understands. I don't even know how to talk to myself to make this problem nice yet. So the moment you embed everything in SU4, you also have the quantum plane relations that have to do with the D terms that capture the reality condition, the fact that you have SO6. So this is super hard. And now I can only efficiently do it for 2 sites. So in 2 sites, for the full SU4 or SO, the 20 prime, the 15, and the 1. The 1 is trivially, there is nothing there to do. Here is the 20 prime, and here is the 15. And what I can I don't show you the calculation because this is still hard. You can go around with, so in this, I have these arrows. So these arrows, on the green, are the ones that we know that they are there and they are unbroken and they should be there. But there are also all the blue arrows. The blue have not been there, yeah? And you make this multiplet, and then you can actually check it also against, you can say time or spin chain diagonalization, and you can do the same, and you can also get it, yeah? So this is, how should I say? If I had tried to do, actually I tried to do 3, but my PhD student wanted to kill me. So there is, I need to think how to make this efficient, yes. So this is the state of the art. Good, so here is a conjecture. Now I'm wrapping up. So I think that what I explained here can be done for any theory with less supersymmetry than n equal to 4, which you can make it an orbifold or an orientifold. Yes? So you really just do the orbifold or the orientifold, and then you marginally deform. And it should, the construction should go identical. The SU4 algebroid should just be there. And then because I only used, by the way, I am insisting in this, I only used n equal to 1 language to do this calculation. So it's not something that should be special about n equal to 2 theories. And this I haven't done, but I also cannot see how not going to the whole thing, you know, I don't see the obstruction, okay, without having done the calculation. And what is important, the important message is that token generators are upgraded algebroid structure. And from string theory, this is really, and this is really this, like this digraph paper. Now, what do we have? We have naively broken generators due to the fold. They come back in the groupoid. The marginal is captured by a Drinfeld twist. The variant and the spectrum, to the degree we can check, lives in representations of this new structure. I have a master student doing general ZK orbifolds, and everything seems to follow. We want to do more multiplets, but I need to think about it in a better way. I think that I clearly don't understand how to use algebroids. And yeah, compare. And then this is also a homework. Now, I said this already, and this is very important. This should play a role for BPS counting. Like indices or Nekrasov or whoever you like, this should be there. Yeah, anyway. So, and again, I think that this were more general. Now, there is this paper. This paper changed a little bit my life when I read it, because when I was reading the older paper, I was not quite understanding at all, basically. Not quite. I was not understanding at all the groupoid sections. But with this paper, I was able to see that he has a Baroque way of talking, but it's the same with me. So his path, a very funny way of talking things, is my path groupoid. It's all the same. You just follow those. And this is really in this paper. This is a very new paper, and I had never read it. And there is another, okay, I will maybe say in the next slide the word. Something else that is very cool, because I have never seen this in physics. There is actually a 2 category. So groupoids, the ones that I described, are 1 category. They combine into a 2 category. Trivially, you follow the arrows, and I am really wondering what the implications of that is. There has to be, at DESY we have this super categorical people, and they immediately write down braiding and stuff if you tell them the category. So I am like, this is my hope now, that my 2 category will do the job. I don't know. And this is a more broad, so this slide is not only about this paper, it's the more broad thing. So what we have nailed in the past is coordinated with all the pain that it takes, and there are these one published already, one coming, heroic papers. My student Denise has led. I cannot tell you what she did, but we did 3 magnons and 4 magnons in a specific vacuum. N equal to 2 spin chains have actually vacua, and there are 2 different ones, and physics looks very different around the different vacuum. And it looks like, even though before in the past, when I was a student, we thought that the Young-Baxter is not satisfied and the system is not integrable, it seems completely wrong, because if you think in the dynamical, what you need to do is you write here your R matrix. You go to the green, you need to write the green R matrix. And when you go to the, what is this color, you need to write that R matrix. So following this logic, there is a new type of Young-Baxter that is actually, and if you really look the way things worked in this paper, basically we were flipping the rapidity of the so that actually we basically make the Young-Baxter come back. Of course, there was a pace to pray. You can ask me questions if you want. Yeah, anyway. And then there is another thing that is happening right now, which is very beautiful. Now that we understand all of this, we are finding that they are higher charges. And they are very cool because you start with, you have a bunch of states with this energy. First, you find that this higher charge exists, and then you act with this guy on this same energy, and it splits them. And usually what happens is that you split, and maybe there is still some energies equal after Q3 acted, and then you act Q5, and then they further split. So there is something going on that is very beautiful, that I don't understand, but it's experimental now, but something exists. Yes? Yes, and with this, thank you. Ευχαριστώ for the Greek organizers. Yes.
In any case, it seems to point to the fact that nothing really will change for the fields on, let's say, the Greenworth action up to boundary. So indeed, it seems that this thing is a twist
Yes.
of what you normally have.
Yeah.
This is the case for the orbitals, so it
Yes.
seems that also for the deformed orbital, it should be the case. So I guess my question is, if it's a twist of some momentum space S matrix, why are you trying to look in position space where it is much more?
So it's just that this is what I knew best. This is how life is. I knew the gauge theory side very well, and I did life with that. And now that I have my postdocs, I try to ask me to go to the other side. That's it.
And maybe a small clarification about the thing that you were saying at the end about these additional higher charges.
Yes. So this is really work in progress.
But you said that they were splitting. So they're all commuting these charges, so they can be simultaneous.
Yeah, they commute, but if you write down your spectrum, what you write at the level of eigenvectors, you find, let's say, I don't know, 4 eigenvectors that have the same eigenvalue. From the Hamiltonian, that's all you know. Then you have found that there is, let's say, a Q3 that commutes with the Hamiltonian, and then you act with that Q3 on this 4 state, and you see that it splits into 2 and 2. I'm just making an example. This is what integrability is supposed to do for you. For now, it's experimental, but it does precisely this splitting. It gives the further structure that you to explain the degeneracy that accidentally is there in the spectrum.
Maybe a final question. So, even if you don't know anything about the theory, you don't know these additional symmetries, categories, all that, the spectrum and the integrable spectra are supposed to look different from the integrable spectrum.
Yes. Yes.
So that's an easy test in principle.
So yes. So I don't want to do numerics. I don't know what to tell you. That's not how I do. No, but I already told you that I have weights, that I do a baby numerics for length 4, 5, 6, because this is my comfort zone, and I find that they're degeneracies, and I find that there is a guy who splits them. So that's my level of comfort, and that's what I do, and I'm happy with it. And someone that knows how to do numerics should do this.
Comment about going beyond large n. We have these degeneracies in the spectrum. I mean, it could be interesting also to look at the 1 over n collection.
Yes. So I think stupidly, because I'm only doing one, I think stupidly the one loop large n and 1 over n is the same. I think afterwards it starts, so that's why I have not even looked. Yeah, it should be in the to-do list. Yes. These two, so the algebroid is made to do this. The algebroid is not just the SU2, let's say. It has this Z2, and this Z2 is the one that makes the cocycle condition work.
So you're saying that...
So it's precisely the one that takes you from yellow to green. That's what it does.
But the cocycle
So it is not the normal Young-Baxter, it's the dynamical version of that. I mean, elliptic books, there is a dynamical version of that that takes you how to yellow to green and so on.
Okay, maybe in view of time, let's and okay, let's put up. Okay, so next speaker is Eric Tonni, who's going to tell us about modular conjugation, entropy, and holographic bit threads.
Thank you. First of all, I want to thank all the organizer for setting up this nice meeting, Lorenzo, Carlos, both Konstantinos and Chiara. And it's very great being here in this beautiful city. So today, I'm going to tell you about some work related to entanglement. So all these, I hope to convince you that all this is what to do with entanglement. And this work has been done together with Michael Mince from Pisa University, Domenico Seminara from and our two students, Stefania from Florence and Francesco Gentile from SISA in Trieste. Like that in this work, the major part has been done by them, by the two students. It's really their work. So this talk is about entanglement, and let me highlight during the past 3 decades. This topic is really has involved 3 big communities here, and there are many keywords that that enters in this game, and on where you start from this triangle is very funny to go to the others, and often is really a question of bridging communities. So there are problems here about entanglement that can be addressed with method here or here, so it's funny to go all over this recycle cycle. And today I'm gonna be, of course we are, I don't wanna go here, I'm gonna stay more or less here. And I wanna stress that in this box here, where many of us sit, there is a community of mathematicians that did a lot of work that can be very useful for the entire program here. And this is called algebraic quantum field theory, and I wanna maybe convince you that I mean using their language can be useful for other things. So first of all, just a brief introduction of basic quantity. So I'm going to talk about entanglement, and so the starting thing is that you take a quantum system in a generic state, for instance, a ground state, and then you have the Hilbert space is factorized at time equals 0, for instance, in two parts, special part, and then the first thing that you do is that you can say, okay, from this the full state of the system, I trace part of the system, what is called reduced density matrix, normalized to 1, his trace is equal to 1. So the key point of all these things is that when you, this tracing procedure give you, even if you start from a pure vector state, this pure state, you get a mixed state. So, oops. Okay, so you get a density matrix, which is a mixed state, is positive, so very similar to a thermal state. So it can be written safely in this exponential form. So if you take the log of this operator, you get what is called Hamiltonian, or in the algebraic quantum field theory language, modular Hamiltonian. So this Ka is an operator that basically encode all the property of this density matrix. Okay. Don't know what's going on, but okay. The spectrum of this operator is called entanglement spectrum. The entanglement entropy is just the von Neumann entropy of this density matrix, which is calculated using by moments, and then you have to take this what is called replica limit, is the derivative index this integer n to this k. So see, something is missing. Anyway, yeah, what is missing here is basically this operator generates so you know, this operator generates a time evolution, which is called modular flow. It is completely different from the usual time evolution associated to the physical Hamiltonian. So you start with a system here, define as an Hamiltonian, is a time evolution that you know very well. Well, now you have another Hamiltonian that depends on the initial state and both on the bipartition, and then you can study the time, call it time, but I call it modular flow, is a time evolution associated to generated by this operator. Okay, it's supposed to be here. Okay, so the outline of my talk is the following. The first part, I will review some known results about in CFT. These two examples I will mainly consider. I will introduce this concept that is, and then the main part is to discuss what is this modular conjugation in both these cases, ground state and thermal state, and concept give you the thermal entropy that we know from CFT for an interval. And then finally I will go in the second part, I will move to the ADS CFT, and I will tell you in this simple setup this modular conjugation is. Okay, so this is one slide of simple from algebraic quantum field theory, so don't get scared, it's very basic, but so what you do, you start with an algebra of operators that are localized in some space-time region, and you have this critical separative vector. Think about the ground state, so this omega, the ground state, and then you introduce an operator which is the basically dagger. So operator O, you associate to the operator the conjugate. So this is formal but very simple to think. Well, this operator, this operator, can be decomposed in functional analysis in what is called polar in a unique way. So this is the operator version of things, the complex number, right? There is the radius and the phase. This is the radius, delta, which is positive definite, it's an operator. And J plays the role of a phase. So in operator length anti-unitary, and in algebraic quantum field theory, this delta modular operator corresponds to what I call Ka before before, but full system. So notice that this delta involves both a complement and this modular conjugation. Yeah, is defined like this. It's anti-unitary, and so this is the modular evolution that I was trying to define before. So you take together and you evolve in a unitary, in the usual way, by this modular Hamiltonian here, right? K. How is the modular time, which is real? Well, the fundamental theorem by Tomita Takesaki that tells that if you start to evolve in this unitary way using this operator, you stay inside, and the A prime is the commutant, so the algebra operator that commute, so that they are space-like separated, right? And then J move between a region to the complement, in algebraic language, to the algebra to this commutant. This is the theorem, and the point is that, of course, beautiful algebraic concept, but is there a geometric way to understand them? Yeah, this is the, you will see, which is the geometric way, but it's not obvious that this evolution here and this J has a geometric action point. If I send a point, I apply the evolution to another point and apply J, it's not obvious that this happens. When this happens, you say that these two operators have a geometric action. Okay. Yes. Yes. This is any QFT, any or n equal to whatever QFT you like. This applies. No. Yeah. What you need? Yeah, you need to start. Yeah, this operator here. Right. It's really super general, and the nice thing is to see explicit example and to see what it means in practice. So that's so this is super general, and now I'm gonna tell you what's happened in 2D CFT. Yes. No, you will see that. See a lot of global stuff. Ask again at the end of the. For instance, the most important example of where is the very famous is due to Bisognano-Wickman in the 75. If you have a QFT in Minkowski, right, and put it in the ground state and split your space in two equal parts. So X1 is this the red part here, relativistic field theory. So this is the Rindler wedge associated to that, and the theorem tells that the modular Hamiltonian Ka is just the Lorentz boost, no? The Lorentz boost that preserves the right Rindler wedge. So the evolution generates are the usual hyperbola that you encounter in the GR courses when you study Unruh effect. Okay. No, this is very bad. Yeah. Sorry. Yeah, you have to think think first thing is to think about the ground state. So you take the ground state of the entire thing. This is typically silicon separating is a condition on the kernel and on the fact that when you have to impose that when you add the algebra on this state, you generate a dense. And then the other condition is about the kernel. So when you, if the state is annihilated by all the elements of the algebra, then so these are the two conditions, right? But yeah.
The other laptop.
No, okay.
mai
Okay, I sit down here, okay. Okay. Then I can point like that. Yes, okay. So we were basically here, right? And the most important example is this Bisognano-Hickman theorem that tells that basically for any quantum field theory, relativistic one in the ground state, when the separation is given by half of the space, the modular of the right part is given by this Lorentz boost. Yeah, the full one is the entire integral over the entire space. So this is the theorem, and in this case, this modular evolution and J, both of them are geometric action. One of them, sigma tau, is the Lorentz, is the generate the trajectory that are the hyperbola followed by you know from Uru effect, and J is just the map one point in the right Rindler wedge into another point into the left Rindler wedge, just with a minus, so reflection with respect to here. So this is the simplest example. The next example is given by CFT in D dimension, and this has been worked out many years ago by Hislop and Longo. They basically realized that if instead of a generic QFT you are in a CFT, you can use maps and send the entire right Rindler wedge here into a double cone of a ball of radius r. So basically you construct the conformal map that sends this geometry into this geometry, and you find the modular Hamiltonian of a ball. T00 is the energy density, as you have realized, and so the interesting thing is that there is this weight function that enters here and characterizes this situation. Then in the case of 1 plus 1 conformal theory, it's again a parabola, but in one dimension, so this gets simpler. And one can somehow consider other cases, or complete cases, finite volume cases, and they all, whenever you have a single interval, basically this is the generic structure of this operator, where you have the energy density here and the weight function here, right? And there are important cases where this is not the case. And as soon as you break this nice structure, immediately you get something complicated, like KA can become non-local and model dependent. So the nice thing about this feature is that it's very universal. You see, it's true for any CFT. While, for instance, if you take massless Dirac field in 1 plus 1 on the line in the ground state, so very simple theory, C equal 1, but A is given by 2 disjoint integral, so just change it. Then this expression is not true anymore, and to add another piece which is non-local, it's complicated, and I want to consider it here. Okay, so this I want to give you the idea to obtain how this formula is obtained in the simplest case of the ground state. So take your CFT in the plane, the Euclidean plane, and the idea is that your interval be around the line for simplicity. The idea is this geometry, in order to study entanglement, you have to introduce a cutoff. And a nice way to introduce cutoff is very well known by string theorists, is to cut out a small disk around the endpoints of these two endpoints. Like this is done in the old days of the worksheet. And if you do that, then a plane with two little disks, you can map this geometry into a cylinder like this. So you open here and you map the entire plane. So boundaries here becomes the two boundaries here, and then you can interpret the Rényi entropies. So this momentum here is the partition of on an annulus like this, but the power here is encoded by opening this cylinder along this line and attaching n copies. So on the numerator, you have the partition function on an n-annulus, so on a bigger normalized in this way, because for n equal 1, it must be equal to 1. Okay, so if you take this approach, you can work out the Renyi entropies and find that, so in this case, W is the length of this cylinder, which is infinite because it depends on this epsilon here. The epsilon is the radius of this, the UV cutoff of this line, of this small disk that you exceed. And so you see that the subleading piece, for instance, are given by the boundary state of the boundary condition, conformal invariant boundary condition that you have to impose here in order to apply this game. And moreover, besides entropies, so notice that for n equal 1 limit you get usual famous result by Wilczek and collaborator. But then in addition you had other information which is about the spectrum. The spectrum in this case can be written in this way, so lambda j are the eigenvalues of this reduced density matrix, and for epsilon goes to 0 can be expanded in this way. And you see that in this expression, beside the central charge, is also the conformal dimensions. Of this boundary conformal field theory, there are two boundaries, one here and one here. So you see the spectrum. So the message is that if you look at this quantity, the also the other conformal data beside the central charge. And sorry, this W, yeah, it's the same. Sorry, it's the same W here. It is written A because it depends on A, but yeah, sorry, this I should correct. Sorry, it's the same W. Okay, this is explicitly in this case. So take the simple integral. This is the case where you start. This is the conformal map that goes from here, for this situation, first into the unit disk and then into a cylinder. So this is identified with this segment, and you find this thing. So I want to emphasize the role of this F. This is the conformal map that sends you from this configuration to this one. Okay, and so this is for the ground state, the same game for the thermal state. You get the map is more complicated. It includes also the inverse temperature, but you still get a local expression. Energy density and the weight function is more complicated. From the length of this cylinder, you find what you expect from the entanglement finite temperature. L is the length of the interval. This expression was found also by using the twist field method by Riccardi in 2004, and they also yes. No, this one in 2D only because you have the exponential map that, fortunately, yeah. That's the difference between, yeah. So the nice observation that I want to highlight here is that what happens at high temperature, no? So at high temperature, as came out also in a nice talk by Romuald, everything becomes kind of classical. So the entanglement entropy becomes a thermal entropy, no? You see, very easy. This beta goes to 0, and beta goes to 0 fast enough. The hyperbolic sign becomes an exponential, kill the log, and you have a volume law. No, so you get actually the famous Stephans-Boltzmann law for the CFT2 that was found by Afflet, Cardi, and collaborators in the 80s. This is the density of entropy. So if you have this is what you write for the thermal entropy in an isolated system of volume L in a CFT2. And let's cover for large, very large at high temperature. Okay. Okay. Now one of the main goals of my talk is to cover this result for any value of the temperature, not only large B. But for this, that's why you need to use this modular conjugation. So in order to do that, I want to introduce another idea, contour for entanglement entropies. Roughly speaking, it's just this expression of entanglement density. So this quantity has been studied first, as far as I know, by Chen and Vidal on the lattice. And basically the idea is that whether it's possible to find the function of the point such that if you integrate over the subregion, region A, in the case 1 integral, you get the entanglement entropy. It's important that this quantity is positive. Of course, this quantity is not uniquely defined. You have to impose various conditions, various constraints that I don't have to here. But if you find this kind of function, you get a spatial structure of entanglement, some quantification of the fact that it is given by the region close by the boundaries. This is a nice slogan, but how you can quantify it? Okay, if you can construct this kind of function, you can quantify. And there are other construction of this kind of entanglement density. But here I want to emphasize this observation that if you take the model constructed in this way, as I discussed before, if you take the prefactor here of the energy density, this weight function, you take the inverse, you integrate over this interval with the little disk exceeded. Well, you get precisely the entanglement. So if you think about the interval case, this is a parabola. So if you integrate one of the parabola, you get a log and get the famous log. So this is an observation. And then you can check, you can construct that, for instance, you can notice that this observation is not, this observation has some lattice counterpart that I don't have time to explain, but if you want, I have some background slide. Basically, if you take, for instance, an infinite harmonic chain, so the harmonic chain with mass omega, there is a lattice way to construct this operator here. And if you compare then this lattice way with this function f that comes from the modular Hamiltonian in the continuum, you see very beautiful here, close to the boundary. And then there is a slight mismatch in the middle. But at least here you see that this divergence captures exactly the log divergence that you expect. And then in this middle is encoding the subleading term that still get a lot of physics. This is the case of finite temperature. So this is a comparison. You see the prefactor here of the entanglement of the modular Hamiltonian. Here's the prefactor, but the match with the lattice data is very nice. And okay, so we have this candidate for this entanglement density, which comes from the modular Hamiltonian. So now what do we do with that? Let's go back a little bit to the modular object that are these. So, and focus on the case of a single interval. Single interval in CFT, suppose that you are in Minkowski. In Minkowski, this is the diamond associated to the interval, and the modular evolution is this kind of trajectory. You start from here and you go here. If you apply the same conformal map Longo you apply to this case, you discover that J comes between the gray region into the blue region. So in particular, you can map this trajectory into this dash trajectory here. If you look at the Euclidean picture, don't have time, you have Euclidean time, and thing is that in Euclidean picture you lose completely this causality thing, because the modular evolution generates some circle in this way. So if you start inside the interval, you follow the modular flow, you go back to the interval. At some point you pass from the complement, and then you go back. This is the Euclidean version of this picture. When you start from this point at tau equals 0, tau equal infinity, you arrive here, and you stop. But then if you go on the, if you want to follow, keep following, you have to, in principle, you have to follow this hyperbola here, go to minus infinity, you arrive here, and you go back, go to plus infinity. So it's much more complicated in Minkowski. But the the observation is that if you start from a point at the interval, you follow the circle, you end to the other point x inverse. It's very simple. It's just given by this simple transformation in this case. The same point that you find here in the Minkowski picture. Okay, fine. Okay, this is the case for the ground state. Now what happens if you play the same game at finite temperature? Euclidean picture at finite temperature, you know we are on the term there. So this is t equals 0, the Euclidean, t equals 0, so the red is the interval. And then you have your thermal circle here. So this dash line is identified by dash line. So you start playing the same game, and you find at some point follow the flow, and you are mapped into the complement. But at some point here, you reach infinity, and you're not mapped into the blue. But in this part, you are mapped side of the cylinder. You go back, and you never touch the complement. This observation is a geometrical observation, so allows you to construct a nice internal interval, A beta, this green region here, made by the point that mapped into the complement, but are mapped in the second kind of thermophile double construction here. Notice that the copy is completely mapped into this green region here. And if you now take your the function that the modular Hamiltonian that gives you the contour rate for the function in CFT, and you integrate not on the entire interval in order to get the entanglement, you integrate only on the green part, you recover the thermal entropy. So somehow what this flow does is to map this proper to the second copy of your theory, and so you recover the thermal entropy inside the entanglement entropy. Yeah, the entangling region is the red. Yeah, here I cannot point, but it goes from here to here. Yeah, so here in order to get the entanglement, you have to put a little disk around the endpoints, right? So if you integrate this function over the entire region, red region, you get, that's why you have to regulate. If you regulate properly, you get the entanglement. But the observation here is that if you integrate instead of this finite part, the thermal entropy. This is, of course, you can say I can always shift, I can always do something, but the observation is that you just take in a straightforward way this constant that comes from the flow, you identify this region and cover the Stefan Boltzmann in this way. What happens in Minkowski? Okay, Minkowski, you can play the same game. You see that the equivalent of this red region is identified by this green diamond here. If you consider modular trajectory here, then you use J, the modular conjugation, and these are mapped. The part is mapped here, is mapped here, and then if you consider the trajectory that passed through this part, you see that they define, for instance, this red part that's mapped into this dashed red thing, and span an entire Minkowski. So the entire green region here is mapped into a second copy of Minkowski. So in some sense here you see what you expect from the thermophile double construction, but extracted from this subsystem. Okay, so this is a purely CFT question, and the question is whether there is a counterpart in holography. Okay, in holography, you know, there is a famous result by Ryutaka and Hanage that okay, the entanglement entropy can be constructed, can be calculated in the minimal area attached to the boundary of your subregion. Very famous formula because it resembles a lot the Bekenstein-Hawking formula horizon, except for the fact that this object here is not the horizon. Okay, there has been various important check. So this formula is now well established. Everybody uses every day. What I want to emphasize here is that when you calculate this object, it is UV divergent, and the UV divergence, you know, people know it. This is a simple example in ADS4. The leading divergence is given by the area law, but then a lot of physics is encoded in the subleading term. For instance, in these simple cases, this PA is the perimeter, is the length of the red curve, but this subleading term, F term, knows about this part, the Ryuta Kanagi surface. And it's very important. For instance, the F theorem is called because this F term gives you the F theorem, which is the 2+ of the C theorem, comes from this part. And then if you change it, for instance, if you go in a black hole, this is the horizon, you see that still this still all, but what changes it is the finite piece. So this part knows about the horizon. And then it knows a lot also about the which kind of region you have. So this example with 3 disks, this expansion still hold in this 3 times this perimeter, but this complicated structure of the Ryuta Kanagi surface can be detected from the subleading term. So there's a lot of physics here, okay? And in particular also the physics that I was describing before is encoded here in this finite piece. What is the idea? Well, the idea is to use a very nice reformulation of Ryuta Kanagi prescription, posted in 2016 by Friedman and Hedrick. The observation is the following, is that the minimal area construction formulating in terms of what are called bit threads. Bit threads are this line here. So what you do is you consider the space of vector fields V mu, which have divergence 0. ADS. So this now is ADS3 for simplicity at equals 0. You consider all these vector fields satisfying this condition that are bounded. The modulus is bounded by 1 or by this constant here, but and why you do that? It's immediate, because if you integrate this condition, you see that the integral of this vector field along a curve here is equal to the flow through the interval, through the subregion. So then you use a theorem of a network, which is called maximal cut-mean flow theorem, and you discover that the same the area of this minimal area can be prescription can be reformulated in this way. So the entropy computed as the maximal of the flow across the interval here. Okay, so you again you have an extremization condition. Now you maximize the flow across the region here. Becomes a problem in the boundary, if you want. No, it's not a point in the boundary, in the minimal surface. The problem in the boundary. And think of this maximization procedure in this way. So, and the role of Ryuta Kanagi surfing is kind of a bottleneck. So basically the flow is here at the bottleneck, but then can be highly non-unique here at the boundary. Okay, and then the observation is that if you now take the flow across this interval, well, this can be a gravitational dual of the contour, no? So, and again, the non-uniqueness of the contour can be translated into many solutions of this problem. The uniqueness is here, Ryuta Kanagi surface, because here the flow is constrained to be orthogonal, like with modulus equal to 1. But here is unique. You can think if you take some cannucce, yeah, this row, and you squeeze them like that. Where you squeeze, they cannot move. but at the endpoint move. And this is the same that happens here. At the bottleneck, they are constrained, they cannot move. Well, here they can move. So here you can construct many ways you can construct these flows, but at the bottleneck, they are unique, they are completely packed. And so, particular, for instance, this nice paper by Iagon, De Boer, Pedrazzo, where they construct various ways. One nice that we like, that I'm going to use, is the so-called geodesic construction. So these integral lines are geodesics, okay? So consider a geodesic. If you do that, and you see, well, that look, this way, this flow give you a way to go from the inside to the outside. And you have many ways to do that. I pick the geodesic one. Okay, this picture this one, except the fact that this is in the bulk and this is in the boundary. And indeed, resemble a lot this picture a lot, only at quantitative level, because if you calculate the endpoint of this green line, well, it's the same endpoint that of this black line in the boundary. So the inverse map that you computed before is the same one given by this geodesic. There is the suggestion is that the geodesic bit threads provide a characterization in the bulk of the geometric action of J boundary. Well, this is for the ground state. What happened at the final temperature for the BTZ? So this is the planar BTZ case. You can construct several analytic expression that I don't report, but they are analytic statistics. Well, also in the bulk, you find this phenomenon that geodesic bit threads, at some point, you find a critical one, the magenta, such that the endpoint is at infinity. And then the geodesic bit thread inside here, up onto the horizon. Well, if you compare the picture to the boundary one that I presented, very similar. Very, very similar. Indeed, the same green interval that you find here is the same green interval that I found before. And if you now take the flow found from the geodesic bit threads in the BTZ brane, you integrate over this interval, you get again the thermal entropy now with the brown and no central charge. So it's a non-trivial check that picture in the boundary is described by this picture in the bulk. Yes, this is superposition of the boundary in the sense that if you take the geodesic that arrive to the horizon, these are the gray one, and if you consider the analytic continuation of them, they arrive here in a tangent way, they are geometrically tangent. If you consider auxiliary geodesic that attach in a smooth way here, well, the endpoint here coincide exactly with the endpoint here in the CFT. This yellow line, same yellow line here. And in this way you can spam the entire second copy. Okay, so the geometric threads, they map the entire horizon into the green region. First comment. Second comment, you map the entire second copy using auxiliary geodesic. Well, in the last 5 minutes, so this is the physical idea that I want to give. And then in this paper, we generalize this idea to higher dimension by considering the Schwarzschild ADS plane. This is the technical background. Well, this problem is complicated because it is basically numerical. Because it's funny that in the simple geometry we don't know the analytic expression of the for sphere. This case is for a sphere. This red curve is numerical, and for d larger than 2 we cannot solve analytically this equation, but still you can do numerical, and that's where Stefania and Francesco did a lot of work. So they construct the geometric bit thread, the geodesic in this case, and what we found here is that you get a similarly the same physical picture, namely you can map. Now this is a disk, and this is the radial direction, the ball in D dimension. And then you can find the thermal entropy in this way. Now it's a volume law, and the entropy is given by this law. And then you can check that you can consider the integral. These are four equivalent expression on different domain of the same integral. This is the integral of the contour in the gray region, in the green region. This is the integral of the flux on the horizon, and then the flux on the second copy when you go back with the auxiliaries. And this is the integral on this part of the Ryuta energy surface, identified by this magenta thing. So all of you can introduce this quantity, and then for the geodesic bit trace construction equal to the thermal entropy. But then you can construct also what happened for other construction. So this is a plot of the profiles of this contour on the horizon and on the second word. Here, the integral below this curve are the same because of this identity, although here is the flux, the support is the entire positive value. And then here is the our numerical result for the thermal entropy compared to the expectation. You see that's numerics, very nice. Size of the green region depending on the dimension, and unfortunately we don't know analytically this curve, but we have some approximation. What I want to conclude is to say that one can construct other connections of bit threads, but this connection we did it in some other type called maximally think, but this relation with thermal entropy is not observed. Particular this quantity, which is the integral between these 2 points, is different from the thermal that comes from the entire horizon. And then I want to conclude with the fact that this construction is very sensible to the global part. So which kind of global your theory you're considering. For instance, instead of considering the brain, you consider the BTZ black hole. First, you decide geodesic do not provide nice construction of bit threads anymore. And this is because this white part, if you start constructing from here geodesic bit, you immediately recover the entire complex, and there are some missing part inside, and so it does not work on this case. So interesting, this work whenever the formula for entanglement entropy is universal. So this is an interesting observation that maybe has some irrelevance, because you know, in this case, when you have finite temperature, finite volume, even in CFT, we don't have a universal formula entropy. So the conclusion is that, so I gave you some example of geometric action for modular objects in CFT2 for an interval, ground state and thermal state, and the fact that conjugation combined with the contour function provide the thermal entropy subregion in the case of an interval. In the SCFT, this constant can be recovered by using the geodesic bit threads, and the construction can be generalized to higher dimension. To way to extend this work, you consider other spatial configuration, other states, other asymptotically ADS backgrounds, and also cases out of equilibrium, both in the boundary, both in the bulk. Thank you for your attention. Yeah, there is a recent couple of years, Rick and Dubeni wrote what they call covariant bit threads, and it's it's much more complicated than this, but it can be constructed. Yes, yeah. Yeah. No, that's a very interesting question related to Yanis. First, you have to use HRT prescription just for the entanglement entropy point of view. That you cut. You have to minimize. You attach to your endpoints and then minimize over the entire geometry. Don't restrict. Yeah, this gives you a covariant way to construct it. Then, of course, one should use this covariant construction for the bitreds, which takes care of entire causal structure of the subregion. And that's, yeah, I don't know how to do, but it would be nice to do it. Yeah. I also would like to see some explicit example of this covariant bitreds. I mean, some like the Bohr, yeah. Mm. The total subsystem very, very small, you mean? In the time dependent, not really, I would say, because even in that case, you use entire time evolution if you think in terms of Aida space-time, for instance. Yeah, either you don't see, if it's too small, you don't see anything, but if it's large enough to see the entire evolution, then you must use this covariant prescription, and yeah, it's a problem to address it.